Good morning, good evening, good afternoon, everybody, wherever you might be. Today is my great honor and pleasure to introduce my brother, my mathematical brother, Jonathan Rosenberg from the University of Maryland. And his talk will be very positive. I mean, that's what we should do before holidays. This will be a very positive talk. Positive scalar curvature on manifolds with boundary. Jonathan, the Zoom is yours. Take it away.
Okay. Thank you very much, Piotr, for the invitation. And I'll take this opportunity to thank all the organizers and wish everybody happy holidays and a happy new year. Okay, so this talk sort of begins with something which probably most of you have heard of before, but then it'll sort of go off in different directions. So just remind you that the scalar curvature of a manifold, a Riemannian manifold, is the double contraction of the curvature tensor. So it's the trace of the Ricci tensor, and it's the simplest curvature invariant there is. Now, one thing we're going to need later, so I'll mention it now, are spin structures on manifolds. So a spin structure, if you have an oriented Riemannian manifold, then on it you have what's called the orthonormal frame bundle. So this is the bundle whose fiber at each point is the set of orthonormal bases for the tangent space at that point. So that's a principal bundle for the group SON, the rotation group. And SON has a double cover, which is called a spin group. So if this bundle has a double cover, which is a principal bundle for the spin group, then that double cover defines what's called a spin structure. And an oriented manifold has a spin structure if and only if the second Stiefel-Whitney class vanishes. So that's basically the obstruction to creating this lifting. And when you have a lift, it's not necessarily unique, but the set of all spin structures that are compatible with the orientation is a principal homogeneous space for H1 of M with Z mod 2 coefficients. So you can think about that this way. When you have one spin structure, something like this classifies the double covers of M, and then you can take your original spin structure and twist it by another cover, and that gives you a different one. And one thing we're going to need later on is that spin manifolds, so that a spin manifold is a manifold together with a spin structure, are oriented for the exceptional homology theories, little ko. This is connective real K theory, and capital Ko, which people in noncommutative geometry are more familiar with. This is ordinary topological K theory, but over the reals rather than the complexes. When you work over the reals, you get finer information. All right, so now what's the interest in spin structures? Well, if you have a Riemannian manifold with a spin structure, then you can define a Dirac operator on it. So I'm not going to be too precise about which Dirac operator I'm using, but strictly speaking, I'm not using the simplest one, but the sort of more complicated one, which is linear for the action of the Clifford algebra on the other side. So that's the one that's needed to get this class in KO homology, which we're going to use. So if you have a spin manifold, then you can define this Dirac operator. So we're assuming we fixed a Riemannian metric. Doesn't matter which metric you choose. But then this operator will have an index which lives in KO sub n because of the fact that it basically gives you a class in KK of C of M, comma, the real Clifford algebra of dimension n. So that's where this KON comes from. So this is is what we'll call the alpha invariant of n. So if n is divisible by 4, this is just the a hat genus, basically. So that's an integer and valued invariant. But when n is 1 or 2 mod 8, then this thing takes torsion values. So this is, we'll think of this as the KO valued index of the Dirac operator. And it's an important fact that this only depends on the spin Borderism class of M. So in other words, if you have two manifolds, and both spin manifolds, and you have a spin manifold of dimension 1 bigger, which has these two manifolds as its two boundary components. So really you put the opposite orientation on one of them so that it's basically a Borderism from M to M prime, then whatever the alpha invariant is on the first manifold is also equal to what it is on the other one. All right, so by the way, please stop me anytime if you have any questions. This should be fairly familiar. There's a classic theorem due originally to Lishnerovitz and then with a refinement by Hitchin, and this was actually Hitchin's thesis. If you take this Dirac operator and compute its square, what you get is something that looks like a Laplacian plus the scalar curvature divided by 4. So I'm using kappa here for the scalar curvature. So that has the following implication, which was noticed by Lishnerovitz. If kappa is strictly positive, this thing over here is a non-negative operator. Its spectrum, it's essentially self-adjoint, and its spectrum lies in the right half line. So if kappa is strictly positive, then this operator has spectrum bounded away from 0, and so all index invariants have to vanish, and then alpha of M has to be 0. The contribution of Hitchin basically was just to use this fancier Dirac operator instead of the original simple-minded operator in order to cover the cases where N is 1 or 2 mod 8. Okay, now in high dimensions, there's a converse if you stick to simply connected manifolds, and that's where the story I want to talk about really begins. So this is a theorem due to Gromoff and Lawson around 1980 with a refinement by Stoltz in 1992. So suppose you have a closed, simply connected manifold of dimension greater than or equal to 5. This dimension restriction, by the way, is essential because funny things happen in dimension 4. If M does not admit a spin structure, then M admits a metric of positive scalar curvature. So I should say right off the bat that the method of proof of this theorem is very indirect. You don't do this directly. You go through certain contortions, which I will talk about in a moment. But anyway, so this is a very deep and indirect theorem. If M does admit a spin structure, then of course we have the obstruction over here that the alpha invariant has to vanish. But what Stoltz eventually proved was that M admits a positive scalar curvature metric if and only if alpha of M is equal to 0. Okay, and again, the method of proof of Stoltz was rather complicated. It's not supposed to be obvious by any means. All right, so since we'll need some of the key ingredients in the proof, let me just mention some. Yeah.
So this converse implication has to be in KO, yes? This is no longer true in ordinary K homology.
Yeah, if it's in K, if you were to use K instead of KO, then you would miss some cases. Yes, right, that's right. Because there are, for example, just to mention the simplest example, if you have an exotic sphere in dimension 9, it's possible for its alpha invariant to be non-zero, even though, of course, its a hat genus is 0. So yeah, this is a necessary refinement in order to get the theorem.
Thank you. Since Lichnerowicz-Hitchin is true for ordinary K homology, this is the easier part, but the converse is
No. What Lichnerowicz did was that if kappa is positive, then the A hat genus is 0. Hitchin's contribution was to observe that it's also true that in dimensions 1 and 2 mod 8, you have a further obstruction. In other words, that this alpha invariant has to be 0, even though it takes torsion values.
Thank you. Thank you.
Okay. Yeah.
But Adam, what do we mean by the converse? You keep on saying the converse, and I see only one way implication in this theorem.
No, the converse, if we assume that this invariant is 0, then the manifold admits positive scalar curvature metric. That's what I meant for a converse.
Okay, so let me tell you a little bit about some of the ingredients that went into Gromoff, Lawson, and Stoltz. Because these, as I said, the methods of proof are very indirect. So the first main ingredient was this Borderism theorem of Gromoff and Lawson. So what they proved was this: suppose you have closed spin manifolds of the same dimension, and suppose M is simply connected. The M prime doesn't have to be simply connected. In fact, M prime doesn't even have to be connected. And you have a spin Borderism from M prime to M. Okay, so as I said, that just means there's a manifold of dimension n+1 that spin that sort of interpolates between them, that has these two as its boundary components. Now, if M prime admits a metric of positive scalar curvature, then you can push the metric across the Borderism and get a metric of positive scalar curvature on M. And this also works when M is non-spin and simply connected, and M prime is oriented and you have an oriented Borderism as opposed to a spin Borderism. Now, for those of you who haven't thought about this before, let me just say where the spin condition comes into this, because from the statement, it's very unclear what spin should have anything to do with this problem at all. So the way you attack this is that you take your Borderism and you break it up using Morse theory into a sequence of elementary surgeries which amount to attaching handles one at a time. So this is a sort of standard technique in differential topology. And the restriction that n is greater than or equal to 5 is the range where the H cobordism theorem works. So that means that you have certain handle cancellation theorems that enable you to simplify the structure of the Borderism so that the Borderisms are of a very standard type. So that's where the dimension restriction comes in. The spin condition comes in for the following reason. A spin structure, this wasn't obvious from the way I defined it, but turns out to be equivalent. The spin condition is basically the statement that you can trivialize the tangent bundle on the 2 skeleton of the manifold. So when the spin condition is satisfied, then you can, then all the 2 spheres embedded in M or in this Borderism between M prime and M, all those 2 spheres have trivial normal bundle. And that is needed in order to construct the kinds of surgeries that you need. In the non-spin case, when M is non-spin, that means there has to be a two-sphere that has non-trivial normal bundle. Now that changes the question of what kinds of surgeries you have to take, and that's where the spin condition comes in. All right, so I won't go into further details on that, but that's just a sort of a little bit of a hint. Now there's another ingredient that Stoltz used for his part of the theorem, which was the fact that if alpha is equal to 0, then M does admit a metric of positive scalar curvature. And that was, he wanted to do something which together with the Borderism theorem would be enough to prove the theorem. So what you need is to construct PSC metrics, positive scalar curvature metrics, on enough spin manifolds to generate the kernel of the alpha invariant. You see, the alpha invariant is a spin Borderism invariant. So that means it's well defined on this thing. This is the group of spin Borderism classes in a particular dimension. And what Stoltz proved basically was that the kernel of alpha is generated by manifolds of a special type that have HP2 bundle structures. So HP2 is the second quaternionic projective space. And that, of course, is a nice manifold of positive curvature. So if you have a manifold which has an HP2 bundle structure, then it's obvious that it has a metric of positive scalar curvature. So that enables you to construct lots of manifolds with PSC metrics in the kernel of alpha, and that's exactly what you need. All right, now, in a non-simply connected case, then the situation is a lot more complicated. And one further complication is that if a manifold is not simply connected, it's possible that it's not spin, but that it has a spin cover. And that case turns out to be much more complicated. So to rule that out, let's make a temporary definition. We'll call a manifold totally non-spin if the universal cover is non-spin. So in this talk from now on, I'm only going to talk about two cases, the spin case and the totally non-spin case. And I won't talk about this intermediate case where the manifold's non-spin but has a spin cover. That basically is a case you're not usually interested in all that often, but it's technically much more complicated. Okay, so here is a theorem which in various forms was proved by various people. Suppose you have a closed oriented manifold of dimension greater than or equal to 5. So then the question of whether or not M admits a PSC metric only depends on the image of the fundamental class in an appropriate homology theory. So in the totally non-spin case, the correct homology theory to take is just ordinary homology. So you just take the ordinary fundamental class of M. That's a homology class in dimension n. And push it forward from M into the classifying space of the fundamental group, because there's always a map from M to the classifying space of the fundamental group, which is an isomorphism on pi1. And you take that map and you just take this class and push it over to there. So the question of whether or not M admits a positive scalar curvature metric only depends on what you get over there. In other words, if you have two different manifolds for which the classes you get are the same, then the answer to the PSC question for one is the same as the answer for the other. In the spin case, however, now we know that the alpha invariant plays a role. So how does that reflected? Well, you have to use K homology, but it turns out that the correct homology theory to take, and this again is a technical complication, which I guess algebraic topologists would understand, but the rest of you probably find rather mysterious, is that what you really need is connective K theory, which is little ko, as opposed to periodic K theory, capital Ko. I mean, in lots of cases, it won't make too much difference which of those two you take, but in general, there's a difference between them. So the theorem of Stoltz and Jung and Führing is that it's just enough to know what the image of the fundamental class of M is in little ko n of the classifying space of the fundamental group.
You want connective ko homology?
Yes, connective ko homology. All right, basically that's because connective ko homology is very closely related to spin Borderism. So spin Borderism, if you localize it, the prime 2 basically has little ko as its lowest summand, and then there's a bunch of higher dimensional stuff. But so little ko is very closely related to spin Borderism, and that's how that comes about.
Well, capital Ko homology, this can be defined in by the
capital Ko is the version of K theory that has Bott periodicity. Little ko does not have Bott periodicity.
Yeah, no, I understand that. The capital Ko homology, this can be defined in terms of spin manifolds using what I call MEPs, geometric cycles.
That's true. Right, but that's because capital Ko is a homomorphic image of little ko. Really, the image of M originally ends up in little ko, and then you can move it from little ko into capital Ko. But right now, I don't want to move it. I want to keep it in little ko. So that's...
Oh, all right. Well, that makes a lot of sense. But okay, I believe that little ko can also be given a kind of an MEP type definition.
Exactly, yes. Yeah, little ko is actually more directly related to spin manifolds than capital Ko because you don't have to build in Bott periodicity, right?
Yeah,
right. So you'd keep the same ingredients, you'd just change the equivalence relation, right?
Well, the tricky part of Paul's construction of capital Ko from spin Borderism is a sort of device for building in Bott periodicity. So you don't want to do that with little ko. Right. Yeah.
Right. That's exactly right.
Yeah.
But I still think it can be done. In fact, I did it, but I don't recall exactly. I don't recall.
Yeah. But anyway, this has been studied by lots of people like
Jonathan, is there an orientation map from spin Borderism to little ko?
Yes. Yeah. So what I call the alpha invariant originally is basically just a map. In fact, it's even a map of ring spectra from spin Borderism to little ko. Yeah.
And could you remind? Go ahead, Paul.
You take spin Borderism, but you change, as Piotr said, you change the equivalence relation. You make it much easier for two manifolds to be equivalent. And also they can have different dimensions. So that will give you a little k, and also capital K, if you do it right.
Okay.
My question was very simple. Could you please remind me again, why is this high dimension needed? So what goes wrong in dimension less than 5?
Oh, so in dimension less than 5, the H cobordism theorem isn't true.
Okay.
So basically what happens is we actually know of counterexamples going back to the theorem of Gromoff and Lawson. We actually know of counterexamples to this statement in dimension 4. Basically, the way you get a counterexample is that you take for example, you can take an algebraic surface of general type, general type in the sense of the Dirac classification, which is simply connected and non-spin, and according to the first statement here, you would expect it to have a metric of positive scalar curvature, but you can show using Seiberg-Witten invariance that it does not. So yeah, the theorem is definitely false in dimension 4.
Okay, yeah, thank you very much. Yes.
Okay.
Sorry, in fact, there are counterexamples for both statements, yes? Since in
Yes,
this theorem,
yes, that's right.
Okay.
Okay, so now, even though it's false in general, there's a statement which is useful to think about, which has come to be known as the Gromoff, Lawson, Rosenberg conjecture. I didn't invent this name, but that seems to be what people call it. But that's basically the statement that if you have a closed manifold of dimension greater than or equal to 5, then it should admit a metric of positive scalar curvature if and only if all index invariants of Dirac operators on M and its covers vanish. So in other words, that the obstructions coming from index theory are the only obstructions to positive scalar curvature. And one consequence of this would be that if M is totally non-spin, it should always admit positive scalar curvature. Now it's known that this is false. Okay, there are counterexamples to this, but still it's a useful statement to keep in mind because there are lots of cases where it's true. So even though it's...
Well, as I recall, Thomas Schick, right, made an important point here about...
Yes, so Schick constructed some counterexamples, yes.
Yes, but however, if you introduce the idea of stably, then I think perhaps this is still correct. I mean, stably means you're allowed to cross with one particular so-called Bott manifold.
That's right, yes. So that the stable conjecture is still quite viable, yes.
I believe this point was made by Thomas Schick, is that right?
Well, Schick constructed some kinds of counterexamples. There were other counterexamples actually already known even from the get-go from Gromoff Lawson, namely, if you take a torus and take a connected sum of a torus with a simply connected manifold that's not spin. So let's say you take T6 and you take a connected sum with CP2 cross S2, then that's totally non-spin. So according to this, it shouldn't, it should have a metric of positive scalar curvature, but by the minimal surface method, you can show that it doesn't. So, I mean, this was always known to be false, but Schick constructed a whole bunch of other types of counterexamples as well in the spin case. Okay,
but stably, if you put in the idea of stably...
But, none of these things are counterexamples to the stable conjecture.
Okay, good. All right.
Yeah.
Good.
Yeah.
Yeah. So okay. You mean there's no known counterexample to the stable conjecture?
That's true, yes.
Good, okay, good. Thank you.
Okay, so now I want to move on and start talking about manifolds with boundary, which was sort of the main thing in the title. So back in their original work, Gromoff and Lawson proved the following theorem, which at the time just seemed to be like a curiosity. So suppose you have a compact manifold with non-empty boundary, and you construct the double of X along the boundary. So that means you take two copies of X and you just glue them together along the boundary. So if X admits a metric of positive scalar curvature that has positive mean curvature on the boundary with respect to the outward pointing normal, then this double admits a positive scalar curvature metric. By the way, let me say something about what positive mean curvature means, because there's some confusion in the literature and there's no agreement on the sign convention. So it's very important to get the sign correct. So what I mean here by positive mean curvature for the boundary is that if you take the boundary and push it further out, the area of the boundary in the appropriate dimension would go up rather than down. Okay, so that's what I mean by positive mean curvature. Some people, unfortunately, have exactly the opposite sign convention. So the literature is very confused on this point. But that's what Gromoff and Lawson meant, and that's what we mean as well.
May I ask you a completely stupid question? I want to make sure I understand this correctly. When you say the double of x along the boundary delta x, so if I take the unit disk, so the double along the boundary would be a sphere?
Correct. Yes.
Okay.
Yes.
Okay. Just to make sure.
In fact, let me just explain why positive mean curvature as opposed to negative mean curvature is important here. So suppose your x is a cylinder, S1 cross an interval. Okay, you can think of that cylinder as being a two-sphere with disks punched out near the north and south poles. Okay, and then as such, of course, it obviously has positive scalar curvature. But in that case, the mean curvature of the boundary is negative, not positive, because if you were to expand the manifold, that would contract these polar ice caps. And so the area of the boundary of the ice cap would go down rather than up. Okay, is that clear to everybody? So think of x as being, let's say, the Earth's surface minus a polar ice cap at each pole. Okay, so that has negative mean curvature along the boundary, because if you push the boundary out in the normal direction, then the area of the boundary, so the boundary is this little
disk.
The boundary is a little circle.
Circle, yes.
Near the pole. So if you push the manifold out, push the boundary out, that actually makes that circle closer to the pole, and that area of the circle would actually, which in this case means length of the circle, would go down, not up. Okay, so that has negative mean curvature. And if you take the double of a cylinder, what you get, of course, is a torus. You take the cylinder and you glue it to itself, attaching the boundary to the boundary. Then you get a torus, and a torus does not admit a metric of positive scalar curvature. So if you change the sign here from positive to negative, this doesn't work.
Why do you get a torus, not the Klein's bottle?
That's a, well, no,
if you have the
there's a convention about how to attach, but you attach x to minus x.
Okay.
Yeah.
Okay.
If you have the sign conventions correct, you'll get a torus.
Yes, you get a torus. But in any event, so the sign here is very important. So if you have positive mean curvature, then M admits a positive scalar curvature. The double admits a positive scalar curvature metric. So this was the theorem of Gromoff and Lawson in 1980. And here's another classic theorem. So this is from Lawson and Michelson in 1984. So suppose you have a compact manifold with non-empty boundary and the dimension's not equal to 4. Again, dimension 4 is exceptional for all kinds of reasons. Then this X admits a Riemannian metric with positive sectional curvature and positive mean curvature along the boundary. If and only if the relative pi1 vanishes. So relative pi1 vanishing means that if X is connected, then the boundary is also connected, and the map on fundamental groups from the induced by the inclusion of the boundary is surjective. Okay, But when those conditions are satisfied, then you can do this. So there are lots of cases, therefore, where you'll have positive sectional curvature with positive mean curvature along the boundary. And then in those cases, you could apply this doubling theorem, and you would get positive scalar curvature on the closed manifold that's gotten by doubling X along the boundary. Okay, if you take these two theorems and put them together. All right, so these are some classical facts. So these were proved back in the 1980s, and then people largely forgot about these things. Something else which it's worth pointing out is that Gromoff proved back in the 1970s that if you don't impose any boundary conditions, then a connected manifold always admits a Riemannian metric with positive scalar curvature as long as the boundary is not empty. That's because of the H principle. Positive scalar curvature for manifolds with boundary only is an interesting question if you impose the right boundary conditions. If you don't impose any boundary conditions, there is no obstruction to anything.
You're saying that any compact manifold with a non-empty boundary.
Yes, always admits a Riemannian metric with positive sectional curvature.
Uh-huh. Okay.
Now, let me mention one of the main ideas in the Lawson-Michelson paper. So Lawson-Michelson, remember, said that in this case, you could construct positive mean curvature along the boundary. So how did they do that? They started with a situation where you have a hypersurface of positive mean curvature, and then you can do surgeries in codimension 2 in the direction of increasing area and create a new hypersurface of positive mean curvature. And by using this surgery process, you can prove the theorem which I mentioned. So just like the Gromoff-Lawson theorem on construction of positive scalar curvature metrics, the Lawson-Michelson theorem also uses the surgery technique. Okay, everybody with me so far? All right, so now let's state the conjectured converse to the Gromoff-Lawson doubling theorem. So remember, Gromoff and Lawson said that if you have a compact manifold with a non-empty boundary, and it has positive scalar curvature and positive mean curvature on the boundary, then the double admits a positive scalar curvature metric. So Shmuel and I, a number of years ago, started asking ourselves, well, is the converse true? So the converse would be this doubling conjecture. Suppose you have a compact manifold with boundary, and suppose the double admits a positive scalar curvature metric, then X admits a positive scalar curvature metric with positive mean curvature on the boundary. That would be the converse to the Gromoff-Lawson doubling theorem. And we call this the doubling conjecture. For a long time, basically very little was known about this. But very recently, this was proved in dimension 3 by Carlotto and Lee. But their methods are very specific to dimension 3, and our focus here is on high dimensions, dimensions bigger than 4. So what they do doesn't really overlap with what we're doing here at all. There's another useful fact, which is worth pointing out, which was proved by Baer and Hanke, and that is that if X is I'm always going to use X for a manifold with boundary and M for the double, just to have a sort of notational. So the X has a positive scalar curvature metric with minimal boundary if and only if it has a positive scalar curvature with positive mean curvature on the boundary. So minimal boundary, I'll remind you, just means the mean curvature of the boundary is equal to 0. So in other words, if the mean curvature is 0, you can perturb it to be positive, and if it's positive, you can perturb it back to be 0. That's basically what Baer and Hunke proved. That's a highly non-trivial theorem, but and it's a very interesting paper of theirs, which I would recommend. But anyway, so this is what they proved.
Sorry, this is in general, yes, for all dimensions.
Yes, this doesn't really, it's a direct construction, basically a careful geometric analysis type argument. You just try perturbing the boundary, and you look at the differential equations that govern the mean curvature, and you just do what you have to do.
So this dimension restriction is only for this result of Carlotto and Lin, yeah?
Right, yes, this is true in all dimensions, the theorem of Baer and Hunke.
Okay, thank you.
All right, so now I want to talk about the doubling conjecture. And so we have some new results on that. So a relatively easy case is the one where X, that's our manifoldless boundary, and each connected component of the boundary is simply connected. But you're allowed to have multiple boundary components. So then this is the theorem. Suppose X and all its boundary components are simply connected, and the dimension is greater than or equal to 6. Why 6? That's because, remember, we saw that you run into trouble in dimension 4, but if n is the dimension of X, then the dimension of the boundary of X is n minus 1, and we're going to need to know something about the boundary too. So we want n minus 1 to be bigger than 4. So that's why we want n to be greater than or equal to 6. Okay, so let's let m be the double. Now, the first statement is that if none of X and the boundary components are spin, then X always admits a positive scalar curvature metric, which is a product metric near the boundary. And also, it always admits a positive scalar curvature with positive mean curvature on the boundary. And the double always admits positive scalar curvature. So all of those statements are all true. If X is spin, then these various conditions are all equivalent to each other, but they're not necessarily automatic. So you also need the vanishing of the fundamental class of M in KO of the fundamental group. Now, by the way, what is the fundamental group in this case? If all X and all its boundary components are simply connected, then when you put them together and form the double, it's easy to see that the fundamental group of the double is a free group. So this classifying space of the fundamental group of M is really just a wedge of circles. So it's very explicit. And then you can show that the vanishing of this class is equivalent to the vanishing of all the alpha invariants of the various boundary components. All right, so let me tell you a little bit about this. As I said, by Van Kampen's theorem, the fundamental group is a free group on k-1 generators, where k is the number of components of the boundary. For example, if k is equal to 1, then the fundamental group is of the boundary is trivial, and the double is simply connected. That's like the case of a disk where the boundary is a sphere of dimension at least 2. Okay, then the double is so if X is a disk and its boundary is a sphere of dimension at least 2, then the double is a sphere, so the double is simply connected. All right, in that case, if k is equal to 1, then the boundary admits positive scalar curvature. Why? Well, in the non-spin case, that's part of the Gromoff-Lawson theorem. Remember, Gromoff-Lawson said that if you have a simply connected non-spin manifold of dimension at least 5, then it always has a metric of positive scalar curvature. But this also holds in the spin case because the boundary of X is a simply connected spin boundary. So since it's a spin boundary and the alpha invariant is a spin Borderism invariant, the alpha invariant of the boundary of X is 0 in that case. Now, sum of the K=1 case is subsumed in Lawson-Michelson because remember, Lawson and Michelson showed that in the case where, let me just go back here to their theorem. So if X and boundary X are both connected and simply connected, then of course this hypothesis here is satisfied. And then you always have a metric on X with positive mean curvature on the boundary. And then of course by Gromoff-Lawson, then you have a metric on the double of positive scalar curvature as well. So you can get a lot of this out of Lawson-Michelson. But the one thing also we would like is to get a metric on X that's a product metric near the boundary. And the way you do that is to start with a standard metric on a disk in the interior of X. So you punch out a little disk in the interior of X. And you start with the standard round metric on Sn-1, which is the boundary of that disk. And then you just push it across the cobordism from Sn-1 to boundary X. And that gives you now a metric on X, which has positive scalar curvature and is a product metric near the boundary. When K is bigger than 1, so K is the number of boundary components, then the M is not necessarily simply connected. In fact, it won't be if K is strictly bigger than 1. So for example, if K is equal to 2, think about the case where X is a sphere across an interval. Okay, that's a cylinder. And then the double in that case is a sphere across a circle. So then you need to assume vanishing of all the alpha invariants. And then if these alpha invariants vanish, you can fix positive scalar curvature metrics on all but one of the boundary components. And then you view X as a cobordism from the disjoint union of those boundary components to the remaining boundary component. And you just push the metric across the cobordism to the last boundary component. As I said, that was the method of proof of the Gromoff-Lawson theorem, and we're using it again here. Okay, so that's the method of proof of this theorem. It's, you know, when you use these techniques, it's not particularly difficult, but as far as I know, this was never observed before. Now let's look at the mixed spin and non-spin case. So if X is spin, then each connected component of the boundary is also spin. Because if you have a spin manifold, it induces a spin structure on the boundary, but the converse fails. So it's possible for the boundary to be spin, but for X not to be spin. For example, I think I mentioned this before, there are exotic spheres in dimensions 1 and 2 mod 8 which don't bound spin manifolds, but they always bound simply connected oriented manifolds. So you could have a situation where X, the boundary of X was an exotic sphere and X was non-spin. All right, so once again, let's suppose X and all the boundary components are simply connected. And let's take the double of X along its boundary and call that M. And we'll assume that X is not spin, but some boundary component is spin. All right, now, if the alpha invariant of such a boundary component is non-zero, then X does not admit a positive scalar curvature metric, which is a product metric near the boundary, because obviously such a metric on X restricts to a positive scalar curvature metric on that boundary component, and we know that such a thing doesn't exist. But nevertheless, you still have a positive scalar curvature metric with positive mean curvature on the boundary, and the double always admits positive scalar curvature. So let's see, how would you go about proving something like this? Well, one case of this actually is also subsumed in Lawson-Michelson. So let me go back to the Lawson-Michelson theorem again. So suppose you're in that case where boundary X is an exotic sphere and X is non-spin, but simply connected. So in that case, this hypothesis is satisfied. So then Lawson-Michelson says you have a metric of positive scalar curvature, in fact, positive sectional curvature, and with positive mean curvature along the boundary. And then applying Gromoff-Lawson, then you get positive scalar curvature on the double. Okay, so already know something about that. In general, if you had more boundary components, then you can use a somewhat similar argument. Basically, what you have to do is, well, you can't apply Lawson-Michelson the way it's stated because that doesn't apply. But what you can do is apply the lemma that went into the proof of the theorem. So in other words, a surgery technique. So that's actually how you prove this. So you don't use the statement of Lawson and Michelson, which I mentioned before, but you use part of the proof, and that enables you to prove this. All right, so let me see if there are any questions at this point. Otherwise, we'll go on. Okay, let's go on to the next thing. So now we want to study positive scalar curvature with a product boundary condition. The question is this: suppose you have a compact connected manifold M. I guess before I called the manifold with boundary X, with non-empty boundary. When does it have a positive scalar curvature metric, which is a product metric in a neighborhood of the boundary? So the idea is to try to duplicate this theorem to the extent possible. Okay, so this said that the answer to this positive scalar curvature question should only depend on the image of the fundamental class in either the homology of the boundary in the totally non-spin case, the oriented totally non-spin case, or the image in little KON of the classifying space of the boundary in the spin case. All right, so let's go back here. Sorry, okay. So here is an analog of that theorem of Stoltz and Young, and this is what it says. So suppose you have a compact connected spin manifold X with non-empty boundary, and you want to know whether it admits a positive scalar curvature metric, which is a product metric in a neighborhood of the boundary. Well, then it only depends on the image of the KO fundamental class under the classifying map in KON of B gamma, B lambda. So here, gamma is the fundamental groupoid of X, and lambda is the fundamental groupoid of the boundary. So let me just say why I'm mentioning groupoids rather than groups here. The problem, of course, is that there can be more than one boundary component. So when there's more than one boundary component, it doesn't make sense to talk about the fundamental group of the boundary, because the boundary has multiple components, and the different components might have different fundamental groups. So of course, you could fix a base point in each boundary component, but those base points don't necessarily behave well when you compare with a base point in X. So a more natural thing to do is to use the fundamental groupoid, which doesn't require a choice of base point. So you always have a fundamental groupoid, and that's always functorial. And in the case where a manifold is connected, then the fundamental groupoid and the fundamental group basically are equivalent to each other as groupoids. So it doesn't make a great deal of difference which one you use. So that's the explanations of why we're using the fundamental groupoid and not the fundamental group here. But anyway, as far as X is concerned, this gamma, could largely be replaced by the fundamental group. The only problem is that you don't have functoriality for the map from the fundamental groupoid of the boundary into the fundamental group of the interior, because you have to make arbitrary choices of base points. So to avoid that, that's why I'm doing this. Okay, so but anyway, so we have this this class over here, and that tells you, if you were to know what this thing is in here, then that class carries all the information you need to know as to whether X admits a positive scalar curvature metric, which is a product metric in the neighborhood of the boundary or not. And there's also something analogous in the totally non-spin case. So suppose X is totally non-spin and each boundary component is also totally non-spin. Then exactly the same thing holds, except you use just ordinary homology. Okay, so you just need to ask, where does the fundamental class of X go in Hn of B gamma rel B lambda, where gamma and lambda are the fundamental groupoids of X and its boundary. So these theorems at least tell us that when the relative homology or the relative KO homology vanishes, then you have a positive scalar curvature metric, which is a product metric near the boundary, which is a highly non-trivial conclusion. Okay, so there's no sort of direct way to prove that, but the surgery method tells you that. But they don't give any clue as to whether this vanishing of the homology is necessary. That might just be an artifact of the proof. But what we do know is that once you can identify the image of the fundamental class in here, then that's enough to answer the question. So in some cases, though, we have a necessary condition. So let me review the main positive result on the Gromoff, Lawson, Rosenberg conjecture. Remember, I told you that that conjecture in general is false, but there's some cases where it's true. So suppose you have a closed spin manifold of dimension at least 5, and pi is the fundamental group, and C is the classifying map from M to the classifying space of the fundamental group. Now, we have little KO and we have capital KO. As I said, they're not the same, but the map from little KO to capital KO just is what you get by inverting the bot element. So in little KO, you have this natural bot element, which lives in dimension 8. And if you invert it, that gives you capital KO. So suppose this, this operation of inverting the bot class is injective. And let's also assume that the assembly map from KO homology of the classifying space to KON of the C-star algebra is injective. Okay, so this thing is known from all the vast research on the Baum-Kahn conjecture in many cases, the injectivity of this assembly map. This thing about injectivity of the periodization map, that's something that's a pure algebraic topology question, which can usually be answered one way or the other in practical cases. So if you know both of these things, then vanishing of the higher alpha invariant is both necessary and sufficient for M to admit a positive scalar curvature metric.
Sorry, may I have a question?
Yeah.
So how strong is this assumption of the injectivity of this periodization map?
Well, it's satisfied for a large number of torsion-free groups. It's essentially never satisfied for groups with torsion for general N. However, there might be specific values of N for which it's true. And you only need that particular, I mean, you only have to check it for the value of N, which is the dimension of the manifold. So even if it fails for some other dimension, if you're interested in a particular manifold, it might be true there, even if it's false in general. Okay, does that answer your question?
So you are saying that there are some possible N's for which this map is injective for every manifold, yes? I understood.
Well, no, I'm saying that if you pick if you give me a group, if the group has torsion, probably this map is not injective for all N, for most values of N, but there might be isolated values of N for which it is. I see. Yeah. I see. Okay, thank you. Okay. If pi is torsion free, then there's a good chance it's actually injective in all cases.
But sorry, N is the dimension of the manifold and also...
N is the dimension of the manifold you're interested in, right, yeah.
Yes, and this map should be injective for this particular N or for each K? Or...
No, just for this particular value of N.
Okay, I see.
That's all you need, yeah.
Okay, thank you.
Yeah.
When you say C star pi, which C star algebra do you have in mind?
Well, I've been vague on purpose because it turns out it doesn't matter which one you take. So injectivity for the max C star algebra in principle is a weaker condition than injectivity for the reduced C star algebra. But,
yes, correct.
So you could even use the max C star algebra if you wanted, and injectivity of that would already be enough.
Actually, in the conjecture of Alencon and me, in the KO form of that conjecture, if there is torsion in pi, then what you've got here is not the left side of the conjecture.
I know.
I'm just saying there's a nuance when there's torsion. Just
I know that, but I'm not talking about your conjecture. I'm talking about the GLR conjecture, which is a different statement.
Yeah.
Okay.
Yes. No, but I think it's interesting.
Right. Yeah.
In your conditions here in the statement, that there appears to be an interesting nuance in both of your conditions when there's torsion in the...
Yeah, when there's torsion, these things are difficult to check. Yeah, and they're usually false, but there are occasionally cases where they're true.
Sure, right. Good.
Yeah. Okay. Okay, so now what we want to do is to extend this to get a necessary condition for X to admit a positive scalar curvature metric, which is a product metric near the boundary.
Sorry, maybe just one stupid question. When you are saying something about the torsion, you mean the torsion of this fundamental group or the torsion of...
torsion in the fundamental group. Torsion in the fundamental group. Yeah.
Okay, thank you.
So if the fundamental groups of the boundary components satisfy the conditions in this theorem over here, then you can apply this theorem to those boundary components, and then you know that the image of the fundamental class of the boundary in KON-1 of the classifying space of the boundary, classifying space of the fundamental groupoid of the boundary has to vanish. Okay, basically, because the boundary is the union of its boundary components. So its fundamental groupoid is the union of the fundamental groupoids of the individual boundary components. So its classifying space, which is only defined up to homotopy anyway, you might as well just take the disjoint union of the classifying spaces of the fundamental groups of the various boundary components. So, this statement over here at least gives us a necessary condition, but that's not enough. I mean, so far this is only looking at the boundary, it's not looking at X at all. So we would like something better than that. And here's what we have to do. So suppose you have a compact spin manifold with non-empty boundary. And we have these fundamental groupoids. So gamma is the fundamental groupoid of X, and lambda is the fundamental groupoid of the boundary. And let's assume injectivity of the periodization and the assembly maps for both gamma and lambda. So there are cases where that will be the case. So then X admits a positive scalar curvature metric, which is a product metric in a neighborhood of the boundary, if and only if the image in here in KON of B gamma rel B lambda is equal to 0. So let me just sort of look at the diagram we're using. So X is a manifold with boundary. So its fundamental group, X is a manifold with boundary. So it has a fundamental class that lives in relative homology, not in absolute homology. Okay, so the fundamental class of X lives in here, KON of X rel boundary X. The fundamental class of boundary X lives in KON minus 1 of boundary X, but we have a long exact sequence here, okay? So we have the fundamental class here, and we have a long exact sequence which goes across like this. Then we have the map C, which is induced by the classifying maps. So you can map this sequence over here to the corresponding sequence for the classifying spaces. And what this theorem is saying is that the existence of a positive scalar curvature metric on X, which is a product type near the boundary, is exactly equivalent to this thing going to 0 over here in this relative group. All right, so this is a very interesting theorem because it uses relative homology in an essential way. So you notice there's the invariant by its nature lives in relative homology. Okay, so that's the theorem. Now, how would you prove something like that? Well, this is where the non-commutative geometry comes in. So this was a long time in coming, but now I'm finally getting to that. So the sufficiency, by the way, was in the previous theorem. So if this thing goes to 0 over here, then because of this theorem back here, then you know that there is a PSC metric, which is a product metric in the neighborhood of the boundary. So we already did the sufficiency, but we need the necessity also. So why does this thing have to go to 0 in order to have a metric of positive scalar curvature? So that's what we're going to discuss next. So suppose X admits a metric which is a PSC metric with product boundary conditions. Okay, so it's a product metric in a neighborhood of the boundary. All right, well, for now, we're not even going to assume that this metric has positive scalar curvature everywhere, just that it's positive scalar curvature near the boundary. Okay, so then if the components of the boundary satisfy the GLR conjecture, then the image of the fundamental class of the boundary in KON-1 of B lambda has to vanish. So let's go back to this. I've replaced, by the way, a little ko by capital Ko, which is okay because the periodization maps were assumed to be injective. All right, so the reason for going to capital Ko is that that's what's more directly connected to index theory. So the fundamental class has to go to 0 in here. And we had this exact sequence here. So if just think of little ko as replaced by capital Ko, and that's the last line here. If this class went to 0 here, then that means it has a lifting back this way, okay, by the long exact sequence. So the image of the fundamental class of X in KON of B gamma B lambda has a lifting to KON of B gamma by the long exact sequence. Now, what is that lifting? We can describe it in very explicit index theoretic terms as follows. So you attach infinite cylinders to each component of the boundary. So let's say you have a component boundary J of X, of the boundary of X, and attach an infinite cylinder. We're given a metric of positive scalar curvature on each boundary component. So we just take the product metric of that metric and the standard metric on the interval. And that gives you a metric on the cylinder, okay? Which matches up with the metric on X near the boundary. So now we have a non-compact manifold. It's X with these cylinders attached. And on all of the cylinders, the scalar curvature is equal to the scalar curvature of the boundary, which was strictly positive. So this is a non-compact manifold, but the scalar curvature is uniformly positive off a compact set. And that's a situation that was studied by Gromoff and Lawson way back in 1980. So this manifold Y has the same fundamental group as X. So we can take its Dirac operator with coefficients in the Mishchenko-Fomenko bundle, whose fibers are rank 1 projective modules over the C-star algebra of the fundamental group, which is, of course, Moridi equivalent to the C-star algebra of lambda, of gamma. So since the scalar curvature was uniformly positive except on a compact set, this Dirac operator is uniformly bounded away from 0 except on a compact set. And so you can show from that it's Fredholm in the Mishchenko-Fomenko sense, and therefore it has a well-defined index in KON of C-star of gamma.
Sorry, you wrote that C-star of pi 1 of X is Morita equivalent to C-star of gamma. Gamma was pi 1 of X or not?
No, gamma is pi of X as opposed to pi 1. So there's a little subtlety here. This is the fundamental groupoid, and this is the fundamental group.
Okay.
So this depends on a choice of base point. That does not.
I see. Okay, thank you.
So the index vanishes if our metric has positive scalar curvature everywhere, because then this Dirac operator is bounded away from 0, not just off a compact set, but everywhere. And the index, by the Mishchenko-Fomenko index theorem, the index is the image under assembly of the class in KON of B gamma. So if the assembly map is injective, that was one of our hypotheses, then this lift to KON of B gamma of C-star of the fundamental class of X vanishes. And so if the periodization map is injective, we get the conclusion in little ko and not just in capital Ko, and therefore this thing vanishes. So that's the proof of necessity. So you notice we're using basically the Gromoff-Lawson relative index theorem, but sort of souped up to the Mischenko-Fomenko setting. And so this is the non-commutative geometry component of the proof. Let's see how we're doing on time. Okay, this is fine. We have still got plenty of time. All right.
15 minutes. Now, 15 minutes.
Yeah. Okay, so let me go back here. So we just proved that under these assumptions, injectivity of the periodization map and injectivity of the assembly map for both gamma and lambda, that you have a necessary and sufficient condition for positive scalar curvature on X with product boundary conditions. So that's really the best possible result as far as product boundary conditions are concerned. Okay, now let me go back to the doubling conjecture. So the doubling conjecture was not about product boundary conditions, but positive mean curvature boundary conditions. So here is a theorem in the spin case. So suppose X is a compact spin manifold of dimension n, and we have to assume n is at least 6, and assume that the fundamental group of X has finite homological dimension less than n and satisfies the bound conjecture with coefficients and the Gromoff-Lawson-Rosenberg conjecture. So, I mean, those are somewhat strong conditions. As I said before, that pretty much rules out fundamental groups with torsion, but the fundamental group could be free abelian, or it could be free, or it could be a surface group, something like that. All right, now let's take the double of X along the boundary. So then the doubling conjecture holds. In other words, M admits a positive scalar curvature metric if and only if X admits a positive scalar curvature metric with positive mean curvature on the boundary. And there's a non-spin version of that also. In the totally non-spin case, if each component of the boundary is totally non-spin and the fundamental group has finite homological dimension, for technical reasons supposed to be less than or equal to n minus 2, don't worry about that so much, then M has a positive scalar curvature metric if and only if X has a positive scalar curvature metric with positive mean curvature on the boundary. Okay, so in other words, the doubling conjecture is true in both of these cases. So I think this is the last slide, but let me now explain where all of this comes from. So to get results on the doubling conjecture, we start with the results on product boundary conditions. Remember, we just talked about how to get a good result on product boundary conditions. So then what you want to do is then apply the method of proof of Lawson-Michelson, this thing over here. As I said, we're not going to use this theorem itself, but we use the method of proof. So the method of proof involves surgeries on the boundary. What was the boundary in our situation? Okay, so you do surgeries. So how is this going to work? So basically what we do is the following. Suppose, let me switch to another screen here. All right, so here's another picture. This is the picture of what goes on in the proof. So basically, what we're going to do is the following. So let's say here's a picture of X, and this is a component of the boundary. So we take a sort of parallel copy of the boundary right inside over here. And now this parallel copy may not have the same fundamental group as X itself, but you can do surgeries on this thing over here to reduce the fundamental group down so that the fundamental group here now injects into the fundamental group of X. And then once you're in that situation, then you're in a position to use the results about product type boundary conditions to construct a metric of positive scalar curvature, not on this, but on this thing with the surgery. So that's the inner red manifold with these sort of green handles attached, okay? So then now you've constructed a metric that's even a product type metric on this sort of smaller copy of X inside here. But now you have to get back to the original boundary. And that's the tricky part. So what you have to do is look at this picture over here. So here's a picture of the double of X. So this is the boundary of X. This is X. The X is the left-hand side of the picture. And the double, this is all schematic, of course. The double is this big egg here, okay? So we started with the boundary of X. We pushed it in. We did some surgeries on it. And then we constructed positive scalar curvature on this piece over here, on this manifold in here. So this is a codimension 1 submanifold inside the double. Now you look at the reflection of this thing across boundary X, and that's this copy over here. So then you have this little region in between, and you think of that as a cobordism from here to here, and you take the metric that you constructed and you push it across the Borderism. So now you've constructed a metric on something a little bit bigger than X that has positive mean curvature. So that has, product type boundary conditions over here. That's not so important because what we're really interested in is the original manifold. So remember, we're trying to prove the doubling conjecture. So we're assuming that we had a metric of positive scalar curvature on the double, and now we want a metric of positive scalar curvature on X, which has positive mean curvature on boundary X. So far, there's no indication of how you do that. But the point is, we have the metric that's of the right type, and now we can put positive mean curvature on this boundary over here by deforming a little bit using the Beer-Hanke trick. And then to go from this manifold over here to this manifold, you do surgeries in the reverse direction. So now we do surgeries to undo the original surgeries to go back from here to here. I know this sounds kind of complicated, and it is, but that's sort of the idea of the proof. So we're doing surgeries on this codimension 1 submanifold to convert it back into this. And now you'll have positive mean, the result of that is that you'll end up with positive mean curvature on boundary X, even though that's not what you had originally. So the proof of this theorem Going back to the theorem again. The proof of the theorem uses this surgery idea. So both the spin and the totally non-spin cases are proved in a kind of a similar way. Basically, what you have to do is you have to start with some situation where you have positive scalar curvature with product boundary conditions. And that you can get using the previous theorem, the one I was just talking about before. Then you go from that to your original situation by doing surgeries to go back. And then you have to use the Lawson-Michelson trick on those surgeries in order to propagate positive mean curvature from one codimension one manifold to another. So that's basically the main idea that's used over here. Technical details are a little bit complicated. I am not going to go into that in great detail, but that's at least a sketch. So maybe it's a good time to wrap up the main part of the talk, and then I can answer questions.
Okay, thank you very much. Let's thank Jonathan for a wonderful talk. And now we have time for questions. So please fire at will.
Jonathan, can
Yes.
you tell us how regulajas, how finite homological dimension comes into all this?
Yeah, so where did the homological dimension come in? Well, in the totally non-spin case, that was fairly evident because remember, vanishing of the image of this fundamental class in here is sufficient to have positive scalar curvature with product type boundary conditions. So if gamma and lambda have low homological dimension, then when you get up to dimension n, which is the actual dimension of the manifold, then this homology group will be 0. So then there's nothing to prove. So that's the main idea. Now in the spin case, it's a little trickier than that, but still knowing something about the homological dimension enables you to control the Tia-Hertzebruch spectral sequence that goes from homology to KO homology. And you still get what you need once you have that assumption. So that's basically where it comes in.
Can I ask something?
Sure,
At some point,
yeah.
you were attaching cylinders to the boundary and then extending the Dirac operator, and you used
Right.
the kind of an equivariant version of the Gromoff Lawson theorem. I think you could also view that index as an APS type index and then use some kind of APS type index theorem. And I was just wondering.
That's true. Yeah. I mean, it's technically easier to do it this way, but it's equivalent. Yes.
Would it be in any way useful to use APS type index theory, like an APS type index formula, or would that be maybe not topological enough or something?
I don't think that helps very much because then you have to estimate the eta invariant and that you know. But anyway, but yeah.
Yeah, all right.
It doesn't make a great deal of difference whether you use APS or this or these cylindrical ends. The cylindrical ends are I think technically easier, but
yeah, thanks.
Sure.
Tomek?
So I have a problem with the computer, but let me ask a question anyway. I have a problem with different types of assumptions in these theorems. Please forgive me if I forgot something from Riemannian geometry, but my question is there any relation between a product metric property along the boundary and the positive mean curvature along the boundary, provided, of course, the matrix on axis has a positive curvature.
Right. Okay. So in general, those two boundary conditions are different. What is true is this. So positive scalar curvature with product type boundary conditions is basically the strongest condition you can impose. When that happens, then of course that implies the weaker fact that now you have positive scalar curvature with minimal boundary, because in the case where you have product type boundary conditions, the boundary is not only minimal, but it's totally geodesic. So product type boundary conditions imply that the boundary is isometrically embedded and totally geodesic, which implies totally geodesic, which implies minimal. And then once you have minimal, then by the deformation trick of Baer and Hanke, you can go from minimal to positive mean curvature and back again by their theorem. So there's a whole bunch of conditions, but the upshot is that having product type boundary conditions implies having positive mean curvature boundary conditions, but not vice versa. You can't go in the other direction.
Mm-hmm. Okay, so the idea is that to compare these two conditions, you need some tricks using topology. It's not a matter of local differential geometry.
Well, the Baer-Hanke theorem is just local differential geometry.
Ah.
They don't use any topology really. They're just using local differential geometry just to deform the metric near the boundary a little bit. But if you have positive scalar curvature with boundary type boundary conditions, product type boundary conditions, then of course that means the boundary has to have positive scalar curvature, and that may not be the case. So that's why in some cases you can show that you can get positive mean curvature, but you can't necessarily get product type boundary conditions.
Okay. So continuing in this vein, can be anything said about the image of the relative fundamental class under the classifying map of the universal covering in the case of positive mean curvature along the boundary?
Oh, if you have positive mean curvature, do you get any conclusion about the relative fundamental class? Not really, no.
Mm-hmm. So your theorem was under this assumption of product structure.
Yes, that requires product type boundary conditions. Yeah. Mm-hmm. So as I said, just to sort of reiterate that the main technique for constructing a boundary with positive mean curvature is to first construct a different manifold whose boundary has product type boundary conditions by changing the boundary a bit and using this theorem. And then you go back from that modified manifold to the original manifold by doing surgeries, and you apply the Lawson-Michelson surgery theorem.
Okay. Can I ask more questions?
Sure, by all means.
Okay. So next question is maybe more speculative. So the Lichnerowicz result is about the implications of positive scalar curvature for the spectral properties of the manifold. What about the converse? Is the positive spectral curvature condition somehow spectral in a sense?
That is a still somewhat unclear situation. So there there are no theorems to that effect, but it's possible that there is some kind of result like that, but it's not obvious how you would do it. It seems to be very tricky.
So some motivation for my question was Alencon's spectral action, when the scalar curvature appears as some asymptotic coefficient, the integral of this.
Right, yeah.
Yeah, so as a measure, somehow it is related to the spectrum of some of the Dirac operator or some other operators.
Yeah, so the integral of scalar curvature, of course, is the basically Riemann-Hilbert action, which controls general relativity. And so, of course, there's a great interest in that, but just knowing that the Dirac operator is bounded away from zero, there doesn't seem to be any direct way to conclude that you have a metric of positive scalar curvature. I don't know any theorems to that effect.
Yeah, sure. Yeah. Okay, so could you say some words about difficulties in dimension 4? Are these problems rather related to problems with surgery or with some obstructions related to self-duality maybe?
Well, so there are lots of things that go wrong in dimension 4, but basically all the methods of proof that rely on surgery go wrong because you don't have enough room to do the surgeries that you want to do. So that's basically what happens. In most cases, you need big codimension for the surgeries, and once you're in dimension 5 and up, that's easy, but in dimension 4, it just doesn't work. So the surgery method doesn't work. Of course, that by itself doesn't tell you that the results are wrong, but it's also true in dimension 4 that positive scalar curvature is closely connected to Seiberg-Witten invariants. And those are actually computable in some cases, and they give you counterexamples to most of the big theorems, like the necessary and sufficient condition for positive scalar curvature in terms of the alpha invariant. So that simply doesn't work in dimension 4. It's known to be false.
Wait, in dimension 4, what, the H cobordism theorem or the S cobordism theorem fails, correct?
Yes. And also the Gromoff-Lawson theorem also fails. So in other words, this not that one, this one.
Okay.
This one over here fails. Yeah.
Yeah.
In both the spin and the non-spin cases, in fact. And still another problem in dimension 4 is that we have absolutely no clue what the classification of smooth manifolds in dimension 4 looks like.
So you said something about exotic spheres, bounding oriented manifolds.
Yes,
but not bounding any spin.
Right. Yeah. So that happens in dimension 9, for example. So it's
much higher dimensions. Okay.
Yeah, it's very easy to construct an example in dimension 9.
So problems with exotic spheres in dimension 4 is irrelevant.
Well, exotic spheres in dimension 4.
Nothing's known about dimension 4 as far as whether there are exotic spheres or not.
It's not known?
No, it's not known.
Oh.
I mean, it's known. I mean, the homeomorphism classification is known, but the diffeomorphism classification we know nothing about. Yeah.
So this is a smooth Poincare conjecture in dimension 4, yes?
The topological Poincare conjecture is true in dimension 4.
Yes, but the smooth version of it is still open. Yes.
Yes.
So, I mean, it's unknown if some reasonable property of the spectrum of Dirac would imply the existence of positive scalar curvature metric. Is that correct?
I believe
this
so.
was asked whether.
Yeah. Yeah.
Is
No, I
there
mean, that's a good question,
there,
but I don't know of anything like that. Yeah.
Uh-huh. That a metric in a neighborhood of the boundaries should be a product metric. I mean, that seems to me a very natural condition. I mean, this
Right.
is
so that's why I like this
condition.
theorem. So,
Yeah.
you know, you look at our theorem over here.
I mean, to have a Riemannian manifold with boundaries.
So, I mean, I think this theorem, well, let's say in the spin case. So I find this theorem very satisfying. So, you know, it tells you exactly what you want to know, really. But or this.
So I have a question about connective.
This one over here, yeah. This is the one.
I have a question about connective KO homology.
Right. Mm-hmm.
If you take connective, let's say KO homology or connective K homology, either one of them. If we have a finite simplicial complex, and we go up high, I mean, we have one group for each non-negative integer. If we go up high, right. I think it just becomes the periodic theory, doesn't it? Isn't that correct? I mean, this is irrelevant for this discussion about positive scalar curvature. I'm just curious about this property.
Yeah, basically. So the Atiyah-Hertzberg spectral sequence for little ko and the one for capital Ko are closely related. So, you know, if you have, I said the Atiyah-Hertzberg spectral sequences for little ko and capital Ko are closely related.
Yes.
So if you know something about the differentials in one, it gives you information about the differentials in the other. But the little ko groups, in the case of, for example, fundamental groups with torsion, can be quite complicated. So
I'm just asking what happens if we have a finite. If you have a finite simplicial complex, the ordinary classical homology, of course, stabilizes. I mean, once you get big, it just becomes zero.
Right. That's where these homological dimension conditions were used. That's right. Yeah, and the same thing is true. So similarly, once the dimension gets up big enough, then the little ko groups will stabilize also. That's right.
And they become the capital Ko groups.
Yes, that's right. Yeah.
Yeah. That's what I was
asking. That's true. Okay. Yeah.
Right. Thank you.
Yeah. So they would be 8 periodic, yes, but up from some n, yes.
Yes. I believe that's
once you get
eventually periodic with period 8. Similarly,
that's right.
Capital.
Yeah.
Okay.
But that's more or less irrelevant for what was going on in this talk today, right?
Right, because you need to know it for a very specific value of n. Right.
Exactly.
So knowing what happens to large n is not going to help you, right? That's right.
Right.
Do these invariants turn out to be invariants of that are finite, or could you just rationalize the whole picture?
No, you do not want to rationalize the whole picture. There's a lot of very interesting torsion information here.
I think it's fairly important to get these kind of precise results that you do not rationalize. I mean, these are very precise results that Jonathan has been discussing. And to get such precise results, it seems to me important to not rationalize. The stable conjecture, stable Gromoff Lawson Rosenberg. That, I believe, is implied by the conjecture of Alain-Kanami. The stable.
Yes, that's true. And by the way, you could form a stable version of this thing also. In other words, if you have a manifold with boundary, you could ask the stable question about whether X cross a bunch of Butt manifolds has a positive scalar curvature metric, which is a product metric in a neighborhood of the boundary. And again, that your conjecture would imply that, yes, in the same way. So it would be a similar statement, yeah. But you have to use the relative homology like this. Yeah.
Right. But in the results you've given here on your slides, these are sort of not stable. These are for the actual manifold that you begin with.
Exactly. Yes, that's right. Yeah.
Right.
Anybody else?
Yes, I have a question. Could you say something about this spin cobordism group, Omega star? I believe it was called Omega star.
Right.
Is it known exactly for any n?
Yes, it was computed by Anderson, Brown, and Peterson in a classic paper in Annals of Math. The nature of the groups is very complicated. So while you can write down in principle a formula for it, it's very complicated. But the structure of the groups is known in the sense that they're direct sums of certain summands of a very specific type. But the counting problem for all these various summands is a little bit complicated.
And it is complicated, in fact, for every n, yes?
Well, the groups get bigger and bigger as n goes up. Basically, what happens is that all of the torsion-free part of spin cobordism comes from some very specific summands for which there is a explicit formula for how many summands there are. So basically, it involves a kind of it involves the number of partitions of so the torsion-free stuff is all in dimension divisible by 4. And if you take the dimension and divide by 4, and the summands are related to the various partitions of that number. So a partition function, grows like e to the square root of n. So, the number of summands goes up pretty rapidly as n gets big. Then there are also some other summands which are sort of sporadic, for which you can write down a generating function for them, but there's no sort of simple pattern.
Well, I think they analyzed it prime by prime, and
there's only one prime of interest in this particular case. So for spin boardism, the only prime of interest is 2.
Yeah, and that was the exceptional one. That was the tough one. That's
yes. At odd prime, spin boardism is the same thing as oriented boardism.
Right. Very good. Okay, good.
Yeah.
So sorry, you are saying that if the dimension is not divisible by 4, there is no torsion-free part. Am I right?
Correct. Yes.
Wow.
But there still could be plenty of torsion. Yeah.
Okay. Thank you. Amazing.
Yeah.
Ludwig, I see you are itching to ask a question.
Yeah, well, I have two primitive questions to the beginning of talk, Jonathan. You said, if I understood correctly, is not the Dirac operator, I know the only one, the Dirac operator, composition of Clifford multiplication with spin covariant derivative. use something else. What are you using? Which operator?
Oh, so what I'm using is the, you mean for this theorem over here?
Yeah, you from the beginning, right? Our indexes were about.
Yes. So what I'm using is the, it's really the Dirac operator with coefficients in the spin bundle that is Clifford linear. So it has a, you have a, the Dirac operator sort of acts on the left and the Clifford algebra acts on the right. So it's the Clifford linear Dirac operator, the one that's discussed in the Lawson-Nicholson book.
Okay.
Well, the vector bundles are the spin vector bundles, the spinor vector bundles. The vector bundles involved. Or the spinor.
Yeah.
But the operator is constructed to be Clifford linear, so that the class of the operator comes out in KKO of C of M comma Clifford algebra in dimension n, which is why you have this class in KON. Yeah.
Okay. Have to.
I mean, you can phrase it in terms of the classical Dirac operator also in some dimensions, but that just is technically more complicated.
Okay. Thank you.
Anybody else?
May I ask a question?
Sure.
What about replacing the spin group by spin C?
Oh, well,
let me continue. For the price, for instance, of tensoring the Dirac operator with some line bundle, complex line bundle.
Oh, so
does it change a lot?
That's an interesting topic, but it's not related to what's in this talk. So, I mean, Botvinnik and I have actually studied this, and there's a kind of theory of twisted positive scalar curvature on spin C manifolds, but it's that's a whole different story. It would go too far afield to explain how that works.
Wait, I have a question.
Go ahead.
There's a difference. If we just go back to old-fashioned oriented and manifolds, there's a difference between oriented and orientable. And for example, the signature of the Hirzebruch operator, the index of the Hirzebruch signature operator is not well defined for orientable manifolds. You have to orient the manifold. I think there might be an analogous thing here. There's a difference between spinnable, that is being able to impose a spin structure, and spin, where you've actually done it.
True.
And that produces different Dirac operators. However, the ambiguity very likely goes away.
The ambiguity does go away because we're only interested in the question of whether the alpha invariant vanishes, and changing the spin structure doesn't change that.
Yeah, good. Okay. Good.
Okay, anybody else? I don't see any raised hands. So in this case...
Sorry, maybe one question related to this last comment. So it could happen that we choose two different spin structures, yes? We end up with different Dirac operators.
Yes.
And a priori, it could happen that for one of these Dirac operators, it could be more or less clear that the index in KO would be 0. And for the other one, maybe it wouldn't be so clear. So one can
no, but actually it turns out,
yeah,
it turns out, so here, this was in the simply connected case. In the case of manifolds with fundamental group, so in the non-simply connected case, what happens basically is that if you fix the orientation, then the different spin structures differ by, as I said, by double coverings. So you twist by a double covering in the manifold, and the effect of that on the Dirac operator is just a tensor with a real line bundle, so the effect on the index is very easy to write down.
I see.
It's a very simple formula for it. Yeah. So as far as vanishing is concerned, it doesn't make any difference.
Mm-hmm. I see. Okay. Thank you.
Okay. I think it's time to wind up 2021. So let's thank Jonathan again for a very exciting talk. And I find it particularly precious, you know, that you have shown to us that our field of study in noncommutative geometry is actually useful in classical, as Paul would put it, old-fashioned differential geometry. And this is the highest test of quality of any subject, if it's any good for other more traditional subjects outside. And so I believe that you proved a very valuable point, and we deeply appreciate it. So thank you again. Thank you all. I hope to see you in 2022. Just let me stop the recording and then continue, okay? Okay, not everything has to go to YouTube, so.
Okay, well, thank you very much for the opportunity, and I appreciate the audience and the questions.
It still works, Piotr, still is recording.